Okay, this is question 9 of the 2014 June FP1 paper. And the question says, prove by induction that for this thing, n, which is a member of, this should be z plus, of all the positive integers, f of n is equal to 8 to the power of n minus 2 to the power of n is always divisible by 6. Okay? So essentially, this is an inductive proof, inductive argument. And there's, I like to think, 4 steps that you have to remember when you're doing a proof by induction. Okay. So here they are, steps. Step 1, you've got to prove it's true for a base case. So that's usually n equals 1. Sometimes if it's a recurrence proof by induction, you'll have to prove it for n equals 2 as well. But you know, it's fairly straightforward. Let's just prove it for a case, and if that's true, then you can move on to the next step. And the next step is the assumption case. Well, not the assumption case. You make an assumption. So that's usually you say, assume a case is true. Let's call that case K. Assume that's true. Okay. Then third step, you do the inductive step. Inductive step, and that is test it out for n equals k plus 1. And essentially, with the inductive step, you want to try and show that the n equals k plus 1 case depends on the previous case being true. Okay? And then if the previous case is true, then it automatically shows that the next case is true. And because you've shown that the base case, when n equals 1, in this case, is true, then the next case, and the next case, and the next case, and the next case, they're all true. Okay? So you've shown it's true for all n. And then final step, which a lot of people forget, but it's actually worth 1 mark in this case, 2 marks in some cases, is your conclusion. Okay, so basically just summing up exactly what I've just said with the inductive argument. Okay, so let's go about trying to prove this. Prove by induction that for all the positive integers, n, that f of n is equal to a to the power of n minus 2 to the power of n is always divisible by 6. So f of n, just write it down again, equals 8 to the power of n minus 2 to the power of n. Okay, so let's test base case. I like to write down, my little steps, because that's just how I've always remembered it. So first step, test the base case. So that's when n equals 1. So let's literally just replace n with 1 and see if that works. We'll see if it is divisible by 6. So f of 1 is going to be equal to the right-hand side, 8 to the power of 1 minus 2 to the power of 1. 8 to the power of 1, of course, just 8. 2 to the power of 1, of course, just 2. So it's effectively just 8 minus 2, which is 6. And of course, it's fairly obvious that 6 is divisible by 6 and goes into 6 exactly once. Okay, so essentially we've shown, right, it's true for n equals 1. It is divisible by 6. Okay, second case, second step is our assumption. And that's, say, n equals k. So assume that n equals k is true. Let's assume that the case when n equals k is divisible by 6. Okay, and that is to say that f of k is equal to 8 to the power of k minus 2 to the power of k. So that's our expression for f of k. Okay, that's all. I've literally just replaced n by k in our original function. Next step is the inductive step. This is where it gets a little bit more involved, with the algebra especially. Okay, and that is just testing n equals k plus 1. And we want to basically show, we want to bear in mind that we want to show that the n equals k plus 1's case depends on the n equals k case. Okay, so let's simply just sub it in. So f of k plus 1 is equal to 8 to the power of k plus 1 minus 2 to the power of k plus 1. Just literally replaced n equals k plus 1 in our original function. No kind of sorcery there. Okay, let's do a little bit of simplification. Let's think back to indices. If you've got 2 to the power of 3 and you multiply it by 2 to the power of 4, that's the same as doing 2 to the power of 3 plus 4, which of course is 2 to the power of 7. Okay, that's essentially what we've got here. 8 to the power of k plus 1, it's almost like in reverse, is equal to 8 to the power of k times 8 to the power of 1. Okay, So it's this thing in reverse. I've literally just here, when we've got a base to some power, and we multiply by the same base to another power, then we just simply add the powers. Okay, and we've still got the same base there. Here I've done it, but kind of in reverse. So we've got a base to some power, and I've split this addition up into separate indices. Okay, so that is what we've done there, and we're going to bear that in mind not to fiddle with it. So this is going to be 8 to the power of k multiplied by 8 to the power of 1. It's exactly the same thing with this 2 to the power of k plus 1. It's going to be 2 to the power of k times 2 to the power of 1. Okay. Now remember what I said just about a couple of minutes ago. We want to show that this n equals k plus 1th case depends on the previous case being true, so the case when n equals k. So we want to make a substitution in here for our n equals kth case. Okay, so let's do a little bit of rearranging with this thing up here with the the n equals k case. So we're going to get, actually I'll write it down here because otherwise I'm going to run out of space. I'm going to actually make a substitution for 8 to the power of k. So 8 to the power of k is going to be equal to f of k plus 2 to the power of k. Okay, and now I can make this substitution in here. Equally, I could have made a substitution for 2 to the power of k. It doesn't really matter. We would have done it exactly the same way. So 2 to the power of k is going to be equal to 8 to the power of k minus f of k. But I'm going to make the substitution for 8 to the power of k. Okay, so 8 to the power of k is going to be equal to... I'm going to actually write the 8 first, because remember we're just multiplying, so we can do it in any order. So 8 multiplied by f of k plus 2 to the power of k, and then I've still got this little thing on the end. So I'm going to actually again just write the 2 first, just because I think it looks a bit neater. 2 to the power of k. Okay, I've done nothing kind of... I've not done anything weird there. All I've done is made a substitution for 8 to the power of k. So let's expand this out. 8 times f of k plus 8 times 2 to the power of k minus 2 times 2 to the power of k. Okay, and this 8 times 2 to the power of k minus 2 times 2 to the power of k. Well, this is 8 times something minus 2 times that same thing. So how many of that thing which I've got now? I've got 6. So I've got 8 times f of k plus 6 times 2 of k. And actually, that's all the hard work done. Okay, because let's look at what this is saying. This thing, f of k, well, in our previous case, in our n equals k case, assumption step, if you like, I've said that I've assumed that the case when n equals k is true. So I've assumed that f of k equals 8 to the power of k minus 2 to the power of k is divisible by 6. Okay, so this thing is divisible by 6. Is divisible by 6, pen wasn't working. Okay, then if you look at this thing, well, that thing is clearly divisible by 6 because I've got 6 multiplying by the front. Okay, so if you multiply by something by 6, then it's obviously going to be divisible by 6 as well. Okay, so this thing is divisible by 6, this first term is divisible by 6, this second term is divisible by 6, so therefore f equals k, f of k plus 1 is also divisible by 6, is also true if, and this is the crucial step, f of k, so the previous case, is divisible by 6. Okay, and now it's just a case of the final few marks, which I'm going to pick up, are done in the conclusion. Okay, basically summarising everything which I've just explained. So, if n equals k is true, then, by induction, n equals k plus 1 is also true. Okay, and I've shown that since the first thing which I did with the base case, n equals 1 is true, is shown to be true, then it must be true for n equals 2, n equals 3, n equals 4, n equals 5. In fact, all n I've shown that it's true, because if it's true for n equals 1, then it must also be true for n equals 2. And if n equals 2 is true, then n equals 3 must also be true. And if n equals 3 is true, then n equals 4 must also be true, and so on and so on and so on. Okay, so since n equals 1 is shown to be true, then f of n is true for all n which is greater than or equal to 1. Okay? You could have said n is a member of the positive integers, but make sure that you define it properly, because if you just write n is a member of the integers, then that also includes 0, and it also includes all the negative numbers, so make sure you include the little plus up here. You could have also said n is a member of the natural numbers. That's absolutely fine. Okay, but let's see where the marks are going to be picked up. It's a 6-mark question. So there's going to be one case, there's going to be 1 mark for testing the base case. Okay, that's a nice simple mark which anybody I think can pick up. Just test a number in there. Okay. There's not going to be any marks for the assumption, but there is going to be 1 mark for testing, for doing the inductive step. So basically finding out f of k plus 1 is equal to this thing. Okay, just writing that down will get you a mark. There will be another mark for substituting the... I'll write it on this side actually. There'll be another mark for substituting the previous n equals k case back into this f of k plus 1 case. Basically trying to show that it's in the inductive step. It's basically showing that this f equals f of k plus 1 case depends on the previous case. Okay, and you get 1 mark for the attempt, and if you do it correctly, you get another mark. So even if you attempt it and you get it wrong, as long as the examiner can see, right, you've tried to do it, you've done it wrong, but you've tried to do it, they'll give you a mark. Okay. There's another mark for showing this thing down here, showing it's divisible by 6. Okay. And then finally, there's another mark at the end for getting the conclusion right. So 6 marks in total. It's not that bad. If you know what you're doing, if you're well practiced with these types of things, it should fall out pretty easily.